Hey everybody, this is Larry. Hit the like button, hit the subscribe button. Let me know how you did on this problem. I'm gonna solve it live right about now. Okay, cool. 45, jump game 2. Given an array of non-negative integers, you are initially positioned at the first index of the array. Each element in the array represents your maximum jump length at that position. Your goal is to reach the last index in the minimum number of jump. Okay. Uh, well, this is actually a very classic dynamic programming problem. Uh, yeah. And you could actually also do this in breadth first search. I guess it depends what n is, but because I guess in the worst case it's n squared, but yeah. Yeah, I mean, I think that's what I have to, that's what I have about saying it. I just want to make sure my index is right. That's what I'm looking at. Your initial first index, you could jump 2 or up to 2, and then yeah. Okay. Um, yeah, okay. DP is, I guess just, I guess infinity is what I want. I just want to set out the Sano values. N plus, I guess n is fine. And I just send infinity to some big number. I just pick a random big number that fits in long. There's no reason about it. And this is just a short way of writing it because I'm lazy. Okay. Yeah, oh, you are not wrong. I've been doing that. I actually do something like this, but I didn't realize that there was a 1 in math because I always thought this is a little bit ugly looking. But yeah, huh. I'll keep that in mind. But I think for now I'm gonna keep this. But okay, fine. Um, that better works. Let me try running it real quick. I say compiling, but not really. Okay. Okay. Whoops, I forgot. But that's fine. So now we want to set the first element to 0 because we started there with no jump. And then now for ix in enumerate nums, I just label this index. So now, yeah, okay. So now for k in range of x, because that's the number of moves you can make, technically is 1 is this, then dp of, actually, why don't I just, no, it's fine. Index plus k is equal to the min of dp index plus k, which is what it used to be, and then the current index plus 1. And yeah, I have to do some bound checking. Hang on. Yeah, if index plus k is less than n, and then now we could just non-negative numbers. So we can always get there. I was just trying to figure out what happens if you can't get there, but cool. Am I right? Yeah, I mean, this is essentially binary. I mean, I call it DP, and this is very DPE, but it's also kind of breadth first search, except for that you always relax from left going to right, and because you're always doing inclusive, because you always want to hit from 1 to the x or whatever that's in the index. So, so yeah, okay. Yeah, let's do it. Can do in one space. Yeah, I was thinking about that during coding. Well, let's see if it works first, I suppose. Maybe I need to optimize this if this is, I can tell the server is slower. Okay. So I don't know what n is, so if n is 2500, I knew that the n square wasn't going to work. So yeah, so maybe we have to do a little bit better. Yeah, this was the naive n square algorithm, and I mean they don't tell you what n is, so I was kind of hoping / guessing a little bit, to be honest. But now we have to think about it a little bit more. Because in effect, what we do here implicitly, what we're doing is that this is actually, I mean, I say that this is n square, but more precisely, this is actually v plus e, where v is the number of vertex, which is n, and the number of edges, which could be all of n square, but not always necessarily. But this is you actually look at each edge exactly once, at least on the very naive graph. So this ends up being n squared, which in this case, yeah, this is a e square, or v plus e, which is n square running time. And unfortunately, they don't tell you the input size, so I just have to guess. But now we have to think about a smarter way to think about this. But clearly, yeah, we have to do a little bit better. I mean, I have some heuristics, but oh, let's see. I feel like I have some heuristics. I think the key one that I just realized, even though I mean I kind of had it in the back of my mind, but the one that I realized was that is an array of non-negative integers, which is maybe obvious, or like I said, like I think I read it. So, but what that means is that you can always go forward no matter what, right? So that in itself, because of that, leads to some sort of maybe greedy. Oh, greedy? Why is it greedy like that? Maybe there's some sort of greedy algorithm that we can think about, right? That we can take advantage of with but how good? And I'm just trying to get it to a place where because it's not necessary that you go to the max number either, because for example, if this is 4 and this is 3, just because 3 is the max number, you can actually just go to the back rate. So stuff like that. But I see. I think so there is a greedy algorithm. I think so. I did the end. So so I think my perspective was that so the reason why I did it this way, which is pseudo BFS, pseudo dynamic programming, is because to be honest, the reason why I did it like that is because, well, one is I didn't know what n was. If I knew n was 2500, then I knew that this was going to run. But because I don't know, I was just optimistic. But the reason why I chose dynamic programming for n square, even though I knew it was n square, is because you don't have to prove anything, right? Like this is guaranteed to be correct in the sense that you're testing every possibility. But actually, there, I think now that I think about it a little bit, and the way that I'm thinking about it is there is a greedy algorithm, and the greedy is some sort of I want to say some sort of it's some sort of like a rolling window, but not really. It's almost like a perimeter type thing. if that makes sense. Like for each, so like if you every number that you process, like maybe there's some way to process the farthest we've gone, or farthest that we're able to go, and then every time that we increment that number, we add one, because it's almost like I forget what it's called, almost like counting overlapping segments or something like that, and then you're trying to get the longest contiguous, but the smallest. Like the fewest overlapping segments to the end, which I guess is a formulation of this problem. But then that means you can't do it greedy, at least not the way that. Oh no. Oh yeah, no, no, you could do it that way. Okay. Yeah, so you could definitely do it greedy. It's like the Z algorithm. You still remember that? I don't know if I remember the Z algorithm. Or jump start. Yeah, I did try to think about jumping it from the end, but I wasn't able to, because you have to, because the number, like you don't have uh, like you have to pre-process the way to get like ancestors of, or parents of the node, right? So that's why I couldn't figure out that way. But now I think I'm doing it. So I would have something like, but yeah, in this case it'll be all one, so extra space. So yeah. So okay, how do I formulate it correctly? Okay, let's say we're current locations at 0. Okay, and then your current max is equal to the numbers of on the first index, right? And then now, okay, let's also set that to next max. And then we could do something like, while current is less than or equal to current max, next max is equal to max of well, I guess, I mean I could do it this way, but oh no, that's fine. So there's another loop, but that's fine. Next max is equal to the max of next max, or the current position plus numbers of current, which is the number of the jump, which is the farthest index that we can go, right? And then we do this loop, and then when this ends, we can set current max is equal to next max, and then you increment counter or jump maybe. Yeah, and then that's it, kind of line. So you have some while loop that kind of loops this together, which is that current max is less than n. Maybe something like that. Oh, I forget to whatchamacallit, increment. Okay. I'm bad with while loops for that reason sometimes. Oh yeah. Okay. Now I got too excited that I forgot how to program. Greedy problems are always a little bit harder for me, for reasons that I talked about that. But oh no. Because the invariant here is, or like as a prop layer, it will always go forward. So, but maybe I've been off by one somewhere. Maybe that. I just wanted that doesn't feel right, but running it is free, I guess. Yeah, that doesn't feel right. Why is it giving me an infinite loop? Do I not? Because this should always be next max should always be bigger because when current is equal to current max, it should still be +1. So that because this is going to be 1 at the worst case, and this is at current max, so next max is going to be current max +1. So that means, All right, let's take out this intense case for a second. And maybe I just add some prints. Okay. Okay, that's actually surprising. 25, but this is, we only look at each number once, so this is linear, in case you're wondering. I mean, so why would this time out? I mean, it's not that many numbers. Oh, non-negative integers, so actually I'm a little bit wrong with the 0. Can this all be zeros though? Then? Oh, you can assume you can always reach the last index. Okay. But the last index could be 0. Well, I guess some index could always be not 0. Okay, let me try this again without the last index, then maybe I could special case it. I actually thought this was positive. I mean, I know that I read it a few times, but I thought it was positive for whatever reason. Yeah, okay. I mean, it's the wrong answer, but also it's definitely way wrong because jump should always be 1. I have to check some other stuff, but this doesn't make sense otherwise. How is this? This always execute this once, right? Unless current max is, unless this is already not true to begin with. Do I already consider myself jumped once? Yeah, I guess so. Okay, fine. Would that mess up my first one? Yeah. No, because you start at 0. So you can't do that. How do I? Okay. Well, I do have an edge case, so give me a second. So you start at 0. You do a jump. No, you still have a jump. So I have an off by one, my first one. That's fine. Let's see why that is. What is this 3? Okay, because 2 it goes to. Let's just put it out. I'm lazy. So 1 it goes to 4. I'm conflating some jumps. That doesn't make sense. That also means that, so now we want to jump to the first one, so yeah. So after 2 jumps, we could be at most at 4. Which is already the end. So I think there's 5 elements. No, 4 is Oh, okay. So this is actually, wow, this is, because you want to get to the last element. Okay, so I just had to off by one. Okay, fine. And not past it. Because very often with these problems, you want to go past it and not at exactly the last one. Okay. Um, and then now we can try this big case again. Just try it. Oh, no, try what? Oh, what does that mean? Oh, oops. What's I'm going to do? Okay, I just run it. Okay, that's a mid 10. Okay, and I'll do a proper explanation if I get it right. I guess that was the one that I I actually was just thinking about this, and then grumble grumble. Actually earlier we talked about empty arrays, and this is the same one essentially, right? Okay, cool. Because you don't need to do any jumps, obviously. But yeah, yeah. So so the reason why I did the n square algorithm first, as I mentioned, is because I could prove to myself very easily that n square algorithm worked because it tried every possible case. But it turns out that this is greedy, and you could do it with all of n. It's just that they didn't give us what the n was, so I didn't think about it that way. I think the more recent problems, and 45, I guess, is a low number. So back in the day, they didn't. But the more recent problems, they definitely give you the n, so then you can kind of make that kind of guesstimation without hand. Though I still have a silly mistake, but that's on me. But yeah, so the idea for me is for the idea behind this one for me is just greedy, and I'll kind of use this as an example as how I arrive about it. So let's have this, and we start here, and we could go 2 steps, right? So I go forward, counting how far I can go, or like what's the next furthest step I can go, right? So here I know that I could jump either here or here, and in here I know that if I jump to here, then the next step after that I could go to position 4, and here I know that I could go to position was it 0, 1, 2 plus 1 is 3. So then we go here instead, right? So this is the next step. So then that's after one jump, and then here, well, we know that the next step is already at the end, so that which is the code here. So then we just kind of, end the while loop. But that's how I kind of thought about it. And this is O of n because you look at each element at most once, which is here. The double while loops. Those while loops are kind of happening in the same time. And as Nel2 would have liked, this is O of 1 in extra constant space because, well, we don't allocate any extra space other than some variables here and there. So that's pretty cool too. Which is, why did I use 14 megs? Is this just Python? But yeah, that's all I have for this problem. And for difficulty, I think the dynamic programming one is actually like a very common-ish problem to be given on an interview because it's like shortest path in a DAG or longest path in a DAG, shortest path in a graph. Those things are all kind of related that I could see it doing. The greedy one, I mean, greedy problems also has its price, though it's a little bit harder on anyways for me because you have to prove it correct. But it's not impossible. So I think this is a little bit tricky if they give you a big enough n that you need to be linear. Obviously, it's harder, but not impossible, but still just hard in general. So I don't know how I feel about that. A competitive program, I need to solve this a little bit faster, to be honest. But they don't tell me the end, so I spent some time doing the dynamic programming part, which I think I got very quickly in theory. I ended up spending 23 minutes, which for hard, I guess is okay. Though I need to cut that down a little bit more in general. But especially for competitive programming. But yeah, I think that's all I have for this problem.